In our last section of Chapter 2, we're going to introduce 6 new functions. These functions are going to be related to our standard trig functions like the sine, the cosine, tangent, and so on. And the purpose of this section is to really try to understand how these functions work, what they look like, what are their derivatives and antiderivatives, so that ultimately if these functions were to ever show up when performing an arc length calculation, or a surface area, or area between curves, or really any of the other questions that we've had throughout Chapter 2, we would be able to tackle those questions successfully. So to understand a little bit more about what these functions are, let's take a look at what our regular trigonometric functions were good for. As I state here, the trigonometric functions that we already know and love, they work really well when we're trying to do trigonometry on a plane. And as I state here, intuitively, a plane is like a flat, infinite, two-dimensional object. So you can almost imagine it like a tabletop that just expands forever out in all directions. Now, that's the way that our original trig functions were defined. They were defined to work on that sort of a flat tabletop surface. But what's very strange is that we don't actually live in a world where everything is a flat surface. And so while trig is a very valuable set of ideas, it doesn't really ultimately become useful in every scenario. So for example, I state down here, the Earth, we obviously know, is roughly a sphere. And so trigonometry on a sphere is very actually different than trigonometry on a flat plane. So another example where trigonometry would be different is if we were working on what we would call a hyperbolic plane. Now a hyperbolic plane might be something that kind of looks like this. You can see here I have this blue kind of saddle-like figure, and that we can kind of see some strange things here. You can see that on a hyperbolic plane, weird things can start to happen. Here I actually have a triangle. It meets the definition of being a triangle. And it is very strange because if you were to look at it, you might be able to see that the angles of this triangle actually don't add up to 180 degrees. That was a property that was dependent on triangles existing in or on a flat plane. You can also see here I have kind of some ideas of parallel lines, which is strange because these lines don't really seem straight. They kind of seem like they curve. And so this is a very weird surface on which to do geometry. But again, just like the Earth is not a flat plane, and so geometry on the Earth's surface is a little bit different than on a tabletop surface, same thing works with a hyperbolic plane. But on a hyperbolic plane, we can introduce our new functions, which we call the hyperbolic functions. Now I have a little picture down here at the right that's going to help us try to understand what exactly these functions are and where they come from. So I'll start by saying this. In hyperbolic trig, what we really say is that for any number t, the point given by these two functions evaluated at t. Here I have something that looks like cosine but with an h on it. I refer to that as the hyperbolic cosine. Here I have a sine with an h on it. That would be the hyperbolic sine. This is a point, and it would lie on the right branch of a hyperbola given by x squared minus y squared is equal to 1. Now this is often referred to as like a unit hyperbola, kind of like how in a plane when we dealt with regular trigonometry we talked about the idea of a unit circle. So here we kind of just have a slightly different shape. You'll see that my point here, which I'm going to underline in blue, corresponds to this blue point that's over here in the picture. Notice I've moved over hyperbolic cosine. In this case, I've used an a instead of a t. And here I've used hyperbolic sine of a as opposed to hyperbolic sine of t, but either or. Now, if I was to go ahead and think about what this point is, or where that point is, I'll be able to say that, again, it lies on that kind of right branch of this hyperbola, which is this kind of two parabola-like shapes kind of facing in opposite directions. And my point's over there on the right-hand side. But it's also going to be the case that this point is such that the signed area of the sector formed by the segment from 0, 0 to 1, 0, the segment from 0, 0 to hyperbolic cosine of t, hyperbolic sine of t, and the arc of the hyperbola, so that is the area of that sector is going to come out as t over 2. Okay, this is a lot of information. It's kind of weird. Notice that what we're describing here is just that this special point is going to be defined to be on the curve at some particular x and y value, right? Some x and some y value is where this point's going to occur. It's given by these new weird functions. And the way that I'll know where to position these is because I want to set up the following area. I'm going to have a line segment that goes from 0, 0 to 1, 0. Notice that's this edge in the picture. I want to go from 0, 0 to my special blue point. That's this edge in the picture. And then I want to follow the arc of the hyperbola, which looks, of course, like this. So I get this red region in here, and I want that region to be equivalent to t over 2. Now, you don't have to worry so much at the moment about why exactly we've selected things in this way, because our goal really here is to see what kind of follows from desiring this. If we actually want to set up things in this way, we might ask if the hyperbolic cosine of some number is some sort of a formula, if it's able to be found in some way, what exactly is it? Right now it's just a set of symbols, but what does it mean? And so it can be proven, and I'll write this here, specifically here it can be proven with ideas from 2.1 actually, that for any real number x, the cosine, or the hyperbolic cosine of x, has the following formula. And very interestingly, it's a formula that involves e raised to different powers. And it looks like this: e to the x plus e to the negative x over 2. The hyperbolic sine, very fortunately, has an extremely similar shape. In fact, it's almost 100% identical, except for the fact that the plus that's in the hyperbolic cosine is replaced with a minus. I always tend to remember that as sine subtract. They both start with s. So this is the hyperbolic sine and cosine functions. Again, I'm never going to ask you to demonstrate where these functions come from, but only to understand these functions in terms of what their graphs look like, what their derivatives and antiderivatives are going to be, and how exactly I can go ahead and evaluate these functions at different points. Now, if you take a look down below, you'll see that in the box here I define actually 4 other hyperbolic trig functions. We have a hyperbolic tangent, which you'll notice is hyperbolic sine over hyperbolic cosine. Just like Regular tangent is sine over cosine. And then I also have very similar relationships with a hyperbolic cosecant, hyperbolic secant, and a hyperbolic cotangent. Oftentimes, you'll hear that sometimes people will choose to kind of shorten the language of saying hyperbolic sine or hyperbolic cosine, and they'll use these kind of shorthands. For hyperbolic cosine, you'll oftentimes hear them say cosh, so somebody might refer to this as cosh x, as opposed to hyperbolic sine of x. And for sine, they might often refer to it as sinh x, as opposed to hyperbolic sine of x. You can feel free to use this language yourself, but I like to make my students aware of these sorts of commonalities that I may not particularly be using often in our class, so that when you go and you hear other people talk about this content, it's not very surprising that they're using different sorts of language to describe it. In the videos to come, we'll take a look again at how exactly we can evaluate these functions at different points, their graphs, and their derivatives and antiderivatives.